Reject.
Okay, hi. My name's Felix. I'm a software engineer working freelance in Prague. And I've come here today to talk to you about rendering 3D content on the web using WebGL. So this presentation is going to be sort of centered around this model that I have here behind me that I made earlier this year to kind of celebrate or commemorate a very important event, and that was Apple finally accepting WebGL as something useful and including it in their desktop and mobile browsers. So this talk is going to be about how you can build something like this yourself using nothing but JavaScript. So this isn't just like a 3D render of something someone's made in Blender. This is just JavaScript code. Okay, so in this talk, I'm going to talk about THREE.js, the library that I used to build this. And then I'm going to actually dive into how something like this can be put together. So what are the sort of primitive objects that you see here on stage? And finally, I'm going to talk a little bit about interactivity. So how it is that you can bring something like this to life rather than just having it be a static render like this. So before I talk about THREE.js, I want to talk a little bit about the underlying technology WebGL and why it's something that you should care about. So for me, one of the really kind of interesting things about the web is the kind of accessibility, the ease with which you can share content with other people. So all you have to do is give someone a URL, and then they follow that and they can see your content. There's no kind of walled garden, there's no app store, no install process, it's just easy. And what WebGL does is it enables this same kind of level of ease of access for 3D content. And this means that people who before wouldn't have been exposed to 3D content, which is normally being stuff in like games or films, can now just easily get to it by just clicking a link. The reason why it's important now is, as I mentioned before, the kind of increasing browser support. And with Apple jumping on board, we have pretty much a complete coverage across all the major browsers, and now pretty much, I don't even know how many millions of iPads and iPods they've sold, but it's a lot. So it's quite exciting. And finally, from a developer's point of view, I find developing WebGL being quite fun, because you have this combination of JavaScript as a high-level language with which you can put together your scene, and GLSL, the code that actually executes on your graphics card, which gives you the power to make some of these special effects work. And I'll talk a little bit about that later. So if you haven't seen much of WebGL, I just recommend this site here called THREE.js.org. That's got a bunch of examples on it. I'll just quickly show you one now. Interesting. It's normally in the day, but today this racetrack is in the night. Okay, I've never seen this happen before, but it's a cool bug. So anyway, when this works, you can kind of see a race car going around the track. I'm not quite sure why it's so dark. But the interesting thing here is that you can just share this with anyone. So if your grandma's into race cars, you can just send this to her, and she can watch the car go round and round the track all day and be happy. Okay, so on to THREE.js. What is THREE.js? So THREE.js is a high-level library for rendering 3D content. The base object that you work with in this 3D world is something called an object 3D. Now, you often don't use this directly, but some kind of subclass. And the most common subclass you'll find is something called a mesh. So a mesh is defined by both a geometry and a material. So a geometry is just a collection of vertices and a set of rules which tells you how those vertices connect to actually make a 3D object. So an example would be a cube where each of the kind of each of the corners is one of these vertices, and the lines that connect those vertices, the edges, are sort of defining how those faces actually connect together. And material is something that you can imagine as like a cloth that you wrap around this geometry to create a 3D object. So this could be like a wood material, or it could be an ice material, or anything like that. So these meshes can then be positioned, rotated, scaled, skewed, all these kind of things within 3D space. But you can also combine them into composite objects. And the way that you do this is that you take one object 3D and add the other object 3Ds or meshes as sort of children, much in the same way that you would if you were kind of building a tree in the DOM. To actually display these object 3Ds, you have to add them to one sort of special object 3D, which is something called a scene. And this is like the root node of your entire scene graph. So it's a bit like the sort of body element in a DOM tree. To actually render a scene, then you need two things. The first is a camera, which again is a subclass of Object3D. So this is something that you just put onto your stage, you can rotate it, you can move it, and you view the scene through this camera. And the second thing you need is a renderer. So this is something that takes the input from the camera and generates sort of a 2D representation of your scene that you can actually show to the user. So how does this look in code? Pretty simple, really. You just create a geometry. In this case, it's a plane geometry, which is just a flat surface of width 600 and height 600. Create some material, combine these two things into a mesh, and add this mesh to the scene. And then you create a camera, add this to the scene, create a renderer, and you're pretty much done. The last remaining step to actually make this something that the user can see is to ask the renderer for a DOM element, and then this can just be appended using JavaScript or jQuery or whatever in the same way as any other element. And then you can move it around using CSS, just like you'd expect. Okay, so I've talked a bit about what THREE.js is. And now I'd like to talk a little bit about why it's something that's fun to work with. So for me, I find the creative bits of building these kind of visualizations or simulations to be what I call sort of the macroscopic and the microscopic level. So what do I mean by that? So the macroscopic level is the stuff that I've been talking about so far. It's your geometries, it's your materials, it's the kind of high-level stuff that describes your whole scene. And then on the other side is the microscopic things. So it's all the kind of really close to the metal code that you're writing that's executing on your GPU. And here you can create a lot of kind of interesting effects. You can write shaders which sort of do calculations based on incoming light or lots and lots of different things. And there's a lot of fiddly stuff in between, which I'm not personally that interested in, and I'm glad that THREE.js solves that problem for me. So I find these kind of the two sweet spots of development in this field. And I often talk to people about, oh, do you want to try WebGL? And they tell me a story about trying OpenGL and getting bored because they couldn't even draw like a rectangle or a triangle because they had to bind buffers to something. Like THREE.js does that for you. You don't have to care. I'd just quickly like to talk about a problem that I had when I was starting out with all this, and that is how do you structure your code on a larger project? So there doesn't really seem to be a de facto solution to this. I mean, a lot of the examples you see on the net with THREE.js are just like, here's one web page, here's 600 lines of JavaScript code, enjoy. And that doesn't really work when you're trying to structure something yourself. So the solution that I've come up with is using Require.js and combining this with THREE.js in such a way that you structure all your kind of functionality into modules. So for example, all my geometry is defined in one file, all my materials are defined in another file, and then depending on when these files need each other, they can just include each other. If this sounds interesting, I've created a sort of sample project here, which just gets you started. This has got nothing in it except a couple of sort of spinning cubes, but it gives you a structure that you can start working with, and you don't have to worry about all the boilerplate. So this is roughly what this looks like. So this is a Require.js module for those of you who aren't kind of familiar with the syntax. And it's reasonably simple. Like we just tell Require.js what we'd like within this module. So here it's the camera, the geometry, the material, the renderer, and the scene. And then we get to use this within this file. So this is an extract from a file, which is the kind of the beginning entry point into our app. So here we have some init function, which takes a mesh and creates that mesh based on a definition of a geometry from the geometry file and a material from the material file, and then finally adds it to a scene. Okay, so that was kind of a quick introduction to THREE.js. Now, specifically, how do we build this thing here? So there's two parts to this section. The first is about the geometries used, and the second one is about the materials. So first of all, geometry. So I've kind of broken up the model here a bit to make it kind of clearer that it's made up of different pieces. And each of these objects that you see on screen is a mesh which has its own geometry. Now, the geometries don't have to be unique. There's not a one-to-one correspondence between the geometry and a mesh. So for example, all these triangles that we have around here, they're the same geometry, but they're a different mesh. So we apply the same triangle geometry, and then we rotate it and scale it and put it into the right place. But they all essentially share the same shape. Okay, so I'd like to talk about some of the geometries that I have here. The first one is pretty boring. It's just a sphere. So the way you create a sphere is you say new 3 sphere geometry and pass some parameters. Pretty easy. So the first one is just the radius, and the second two here specify how many vertices our shape is going to have. It kind of tells us how many horizontal slices and vertical slices this object is going to have. The second one is, again, a primitive shape, so it's a torus. Here the first two parameters specify the radius and the thickness of the ring. And again, the last two are specifying how many vertices we have. And this is quite a common way of making geometries in THREE.js, that you kind of tell it how, given a sort of a simple shape, how it should separate it into actually sort of discrete vertices. And here the choice is basically just a trade-off. I mean, do you have a high-performance application which isn't very accurate, or do you have one which is very kind of physically accurate but runs slower? Okay, so the next geometry is something a little bit more interesting, and I use this technique quite a lot in this model because it has circular symmetry. So this is using something called a lathe geometry, and this is using, I'm talking here about this ring that we have in the center here, so not the spikes that are coming out of it, just the round ring. The way this is defined is that you tell THREE.js that you would like to take 2 points that are separated by each other by some distance, as the thickness of this ring, and then you'd like to rotate those 2 points around a center to create a geometry in that way. So rather than defining the whole shape, you define the cross-section and then spin that around to give you a solid shape. Now, you can do this with more complicated cross-sections to give you something that's actually a 3D shape rather than a flat 2D shape. And I actually do this for the outside of this compass. So while this may look almost like the torus geometry I showed you a second ago, it actually has a sort of flat surface down here, so the glass has something to sit on. So the cross-section of this is like a circle, except that it has a little notch in it. And you define this by just drawing a couple of lines and then having an arc which kind of loops around. Finally, a text geometry. This should be pretty self-explanatory. You pass in some text and you get out a geometry. And this is pretty much it. There's not much more to making this model. Like using all these primitive shapes and scaling them or squashing them, you can actually get an object which looks reasonably realistic. So now I'd like to talk a little bit about the materials used here, which I think is a bit more interesting. So just like with geometries, the materials can be shared between different objects. So for example, this top bit here, both these objects have the same material, at least when the side thing isn't flashing, as the outside of this. And the materials can also be updated on a live object within the scene at runtime, as you can see here. So the first material I'd like to talk about is just wireframe material. So this is mainly useful for debugging. I've used it here when I'm sort of highlighting different portions of the app, but most of the time it just kind of makes for a reasonably boring shape. The first material you might actually want to use is something called mesh basic material. And this just uses a solid color. So it doesn't have any kind of shading. It doesn't do any calculations with light. It just colors every pixel with a single color if it's within that shape. The shadows that you see on top of here are added later, so that's not part of that material. Now, this doesn't actually look very great. So most of the time, you want to use something called a mesh Phong material, which actually takes into account lighting that you have within your scene. So just like we added a camera to our scene, you can also add lights, and those can be positioned and moved around your scene. So what the mesh Phong material does is it sort of takes in the position of the camera, the position of the light, and then the position and the normal of the surface. And from this, it calculates what color it should use. And it does this in such a way that you get this nice effect where sort of hidden bits of the object, the darker, those that are directly illuminated have the correct color. And then you also get what's called a specular highlight, which is where the light is coming in directly and bouncing straight into the camera. Now, this is using a solid color as a base, and most of the time you'd want to use something like a texture to give it sort of more realism. And to do this, you just pass in an extra parameter into this mesh Phong material, which is just a texture. In this case, it's this wood texture that I have here. Okay, so all of this you probably could have guessed. I mean, how else would I have done it? So I'd like to talk about some of the more kind of advanced things you can do with materials, which I think really bring this model to life. So the first one is something called an environment map. So here you specify a texture, in this case, this sky image, which isn't going to be applied directly to our object. But what the shader actually does is it creates kind of an imaginary cube that's surrounding our scene. It applies this environment map to the inside of it, as if it was like the background. And then when it calculates, when it's rendering the actual object, it calculates what would have been sort of the bouncing off effect, as if this thing was a mirror, onto the environment. So you get this nice kind of glossy, metal-like appearance to your material. Next one is something called a bump map. So this is, again, another texture that you pass to your material, but isn't used directly onto the surface. It's kind of describing the small-scale deformations of a surface. So here I have this demo kind of oscillating between kind of a very coarse bump map and no bump map at all to show how this material changes. And it really gives a very kind of different feeling to what your material looks like. So in this example, this is actually using both an environment map and a bump map. So the two things can be combined. And THREE.js is clever enough to know that it should sort of deflect the rays according to the bump map to give you something that looks quite realistic with pretty much next to no code. So the last bit of the puzzle is how do you make something that's kind of glass-like? Here the difficulty is that you have an object that has to have some transparency, basically. So far, everything we've been rendering has been completely opaque. So if one object is in front of another object, you can't see behind it. THREE.js lets you, again, still with a mesh fong material, say that, yes, it's going to be transparent. How transparent is it going to be? And then the trick to making something look like glass is using the correct blend mode so that you combine the pixels of the object in the foreground with that in the background. And there's no kind of exact science here. Often it's just a matter of playing with the parameters until the thing looks right. Okay, so that was everything on geometries and materials. Now I'd like to talk a bit about how you actually move this thing around on stage. How do you make it something that kind of feels like it isn't just a static object, because then you might as well use a JPEG. So first of all, lights. A light is just something that you create in the same way that you might any other object on the scene. It's another descendant of Object 3D. You can position it, you can move it. And in this demo, I actually have the light moving a lot more than it does in the other ones to show the kind of effect that it has on the shadows and all the reflections and all that. This interacts with some materials, not all of them. So for example, the basic mesh material that I showed you, it doesn't care about lights. It just colors everything with 1 pixel. But on the other hand, the mesh fong material, if you have no lights, you have no object. So they are quite important. So interactivity. How do we make our scene kind of move? How do we make it something the user can play around with? The solution is pretty obvious. You basically have some function that is called again and again and again, and every time you change something and re-render. The one gotcha here is that you want to be using a function called request animation frame rather than set timeout, because request animation frame is something that the browser will schedule at the right interval to give you something that performs smoothly, rather than set timeout where it will try and call it quickly, and your browser might not be able to keep up. So as an example, I'm going to show how you can make the camera sort of zoom in and out. So we have our render function here, which is called on every frame using set animation frame. We have a clock, which THREE.js just provides for us. And on every frame, we calculate a time. We pass this through some math function, which is basically something that's oscillating backwards and forwards. We set the camera position based on this, and we're done. Or not quite. The one thing that we're missing is that the camera, if it's moved, might not be pointing at the right location. So the one thing that we still need to do is tell it to look at the right object. But once we have this in place, it's very easy to get our scene looking right. The actual function that I use in this example is a little bit more involved, but again, it's just maths. So here we're combining the x and y position into like an orbital motion, so we kind of go round and round the object. And then the height is something that kind of goes up and down at a slightly different frequency, so it's not too repetitive. Okay. Finally, you don't have to use time as the input into your interactivity. You can also use user input, so the mouse or the keyboard or anything you think of. You could probably use a network event if you wanted to. So here I have left and right movement sort of mapped to moving left and right, and up and down giving us a zoom. And you can also click, and it spins this thing in the center. But obviously, you could do more. Okay. I see I still have some time left. So I mentioned GLSL earlier as the sort of shading language that you use on graphics, on the graphics card. And I'd just like to quickly point out some tool that Firefox recently shipped that gives you quite an easy way to play around with GLSL without actually having to understand that much. So I'm going to swap out of Safari and go into Firefox. And I have this demo loaded up here, which I didn't make, which is just of some Formula car. And in the Firefox DevTools, you can, when you load this up, there's one tab which came out maybe a couple of months ago called a shader editor. And what this lets you do is look at all the shaders that this particular graphics program is using and edit them in real time, which I think is pretty cool. So as you move through, it will highlight different objects. So here, for example, we'll highlight the helmet. And what is a shader program? So it's composed of two portions, the vertex shader, which is more to do with the geometry, and the fragment shader, which is to do with drawing every individual pixel. So here, what I'm going to do is just look into the vertex shader and play around with it. Now, normally when you look at this code, it looks like junk. There's a lot of stuff there, so I don't expect you to understand it all. But if you look around, you can often find little bits that you can play with. So for example here, this is quite obviously just the position of this guy's helmet. So one thing I could do is just add a bit to it and move the helmet out. And you can do this with all the stuff there. Similarly, if I'd want to do something in the fragment shader, which is more to do with the colors. So let me just find something interesting. Sadly, these programs always have a different number depending on what order they load in. Yeah, so this is the car itself. So here what I can do is I let the shader do all its calculation. And the way these shaders work is that they, at the end, set some sort of parameter. So in the case of a vertex shader, they set GL position, and that's what's rendered. And in the case of the fragment shader, they set GL frag color. And then if you play around with this as the last thing, then you can sort of change it. So here what I'm going to do is take the red and green channels and then just swap them around, which should change the color of the car. And it does. Okay. Cool. Yeah, that's pretty much all I have. So I hope you enjoyed the talk, and I hope you enjoyed Reject.JS.
Reject.